Hello, and welcome to Project 3.3, the Keypad Matrix Echo. This project is the first to use the AT-Tiny84, the purpose of which is to display a mirror image of a keypad on an LED matrix. This is a keypad matrix from a telephone, a 4x3 one to be exact. It's written in rows, 4 rows, and columns, 3 columns. It shares a common pin. When a button is pressed, that common pin gets connected to whatever row and column it is. This is the common pin furthest to the right. For example, if I were to press 5, the middle column and second from the top row get connected to the common pin. That's how the Tiny84 code works. Firstly, in the setup section, here, it first sets the data direction register, or what we generally consider to be the input-output register, to set the data pin, latch pin, and clock pin all to high, allowing them to be outputs. Now, what I've defined as the data pins, clock pin, and register pin are actually one shift left of the actual pin. What this does is it activates the respective pin for the port it's working with. After that, I set port A to all have pull-up resistors. Since the natural state is for it to always be in input mode, I do not have to set it to be input mode in my setup. After that, it's port B NAND the latch register. What this does is it sets the latch register pin to low. After that, I have my shift-out statement. My shift-out statement increments 7 times because I'm only sending 7 bits. It's much faster this way and less wasteful than sending that 1 extra bit. So, from starting at 0 and all the way to 7, if the pin A XORed with the input mask, what the XORed with the input mask means is that I'm going to try invert the row bits here. This is much easier than doing some complicated bit masking. What I can just really do is just XOR it with a simple bit mask. Now, it's then ANDed with one shift left the bit that's being dealt with. What this means is that it's going to deactivate or delete all the other bits than the one that's supposed to be sent out. It's then logically knotted twice. What it does is a logical knot is it takes something like an 8-bit value. If anything is high at all, it's going to be high. Well, low, because it's a logical knot. Now, knotting a knot is just the same as normal. So what the 2 knots does is essentially it converts it to a boolean. Now, if that boolean is equals to high, well, set the data pin to high. Well, if it's not high, it's a boolean, that means it must be low. So it must NAND it or set the data pin low, as you can see right here. After each time, either it's high or low, the clock pin is pulsed. So high, low, as you can see right here. After that, that increments 7 times. So that each time it increments by 1, all the way to the desired number of bits needed. Then it's this latch pin to high, low, high, my bad. And that completes the shift-out statement. After that, it delays for 300 milliseconds, so you can see your button press even if you let go pretty fast.